So hello everyone, my name is Cesar Chaves. I'm doing a cooperative PhD between TalTech and Frankfurt University of Applied Sciences, which is sponsored by the German Academic Exchange Service. This project is supervised by Professor Thomas Holstein from both universities and co-supervised by Johanna Sepulveda from Airbus and TUM. So today I will give you a brief overview of all the work we've done so far. And the title of this presentation is Towards the Mitigation of Communication Threats in NoC-Based Multi-tenant MPSoCs. So the outline for the presentation, we'll see first an introduction with some basic concepts. Then the objective of the current work. I will then present some of the threats that we have identified so far, then what others have done regarding these threats. Then we will go one by one of the 4 approaches that we've published so far. Then conclusion and future work. So first of all, a multiprocessor system on chip is an array of processing elements that are connected through a communication structure. And these processing elements can be processors, hardware accelerators, memories, peripherals, or any other intellectual property. And when you want to integrate several of these processing elements, you will use network on chip because of its scalability. And then you will have these routers connected by network links. And you will also have network interfaces. The network interfaces will get data from the processing elements and encapsulate this data into packets, as you see here on the bottom left. These packets are divided into flits, which are a group of bits that are transmitted at the same time on one clock cycle. So you have here a header flit that will have at least the information regarding the destination address. You will have some data about the packet, maybe packet size, packet ID. Then you will have some body flits with the payload of the message and a tail flit to symbolize the ending of the packet. So once it is encapsulated, the packet is sent to the router. Then based on the source address, destination address, and the current routing algorithm, the router takes the decision to which of its neighbor it should forward this packet. And then the neighbor will send it to the next neighbor and so on until it reaches the destination. Once it gets to the destination, another network interface will decapsulate this data and give it to the processing element. Okay, so we are focusing on NoC-based multi-tenant MPSoCs, and in this context, we will have some users that will submit their applications to the execution environment, which could be fog, cloud, or whatever. And in this execution environment, the shared resources will not only be general purpose processors or servers, but it will also include MPSoC powered devices. So users submit their applications, then a task scheduler will, depending on the characteristics of each of these applications, will schedule some tasks to MPSoCs. The MPSoCs will execute these tasks, and then the results will be gathered and sent back to the user. So at some point of this execution from the different users, we will have tasks from more than one user executing in the same processing element. In the same MPSoC. So another thing we need to have clear is this how packets are switched. So we don't want this network on chip to have a great area. So instead of having big buffers inside each of the routers, which get the entire packet, receive the packet, and then sends it to the next router and so on, we can take the routing decision only with the header flit by using this wormhole switching. Since we already know that the destination address is in the header, we could just take this decision forward to the next router, and then we will have a situation like this, in which a packet is divided several routers until the tail fleet arrives. And then when it does, the path is released for any other packets that wish to enter the same path. As for example, you see here at the bottom that other 3 packets are waiting to use the same output, the east output, while this red packet is being forwarded. Another important thing and good practice for this networks on chip is fair arbitration, such as packet-based round robin, in which it lets only one packet of each input port through each of the outputs when there's a competition. So in this case, it would let a red, then a green packet, yellow, and then starts again. Okay, so now communication threats that target this type MPSoCs would be tampering, which will include, for example, inserting Trojans in the router that will get the data, and once it's activated, it might just drop the packet or change the destination address or corrupt the data in it. But what we focus on are bandwidth attacks, in which a task running on any other processing element injects traffic that will collide with the other genuine traffic and will prevent it from reaching its destination in the desired time. So the end-to-end delay will increase. So having said this, you may notice now that once the attacker gets a grant of one of the output ports, it will try to remain that the grant will still be his or hers as much time as possible, so that the others will have to wait. So with this in mind, the objective of the current work is to detect and mitigate communication threats targeting the bandwidth of NoC-based multi-tenant MPSoCs. So far, we identified 4 types of attacks, which could be classified into 2 groups. The first one is floating denial of service attacks, which are the most common in the literature, especially the first one, which is the packet injection rate, which, since we are attempting to flood the network with data, then what it does is the attacker sends as many packets as it can. So if you compare it to the normal transmission, you will see that we will have more packets. The size of the packets will remain the same or more or less the same, but we will have more packets. The second attack would be this packet payload length based attack, which will also send lots of data, but in longer packets instead of many packets. Then these low and slow DOS attacks, we've adopted them from TCP/IP NoCs, and this first one is packets. So as I said before, the path is secure for a packet until the tail fleet arrives. Doesn't send a tail fleet. Then we have the jellyfish interfleet delay, which sends packets that are the same size as the normal. However, it injects some delays in between the fleets. And you can see here by the figure that if this is equivalent to this packet payload length based floating DOS attack. Since even though it has less data, the tail fleet arrives at the same time. Okay, so related work, we could classify it into 2 parts. One is the approaches that attempt to completely avoid the denial of service, and the other ones that try to detect it and then mitigate it. So in the first part, we can find the use of virtual channels, so that packets are tagged or labeled inside the router. And once a packet is no longer able to be forwarded to an output, then it gives the turn um, to the other packet using the same wire. Okay, another approach is circuit switching and packet switching. So what it does is that sensitive packets will use circuit switching, and then they will have a secure path for all its transmission, while other packets will have to go around this path. And lastly, we have secure zones. So some zones are allocated inside the MPSoC, and within this zone, only the sensitive packets can flow. So these packets are isolated from the malicious ones. Okay, the good thing about these approaches is that they completely eliminate the vulnerability to denial of service. However, some of them reduce the system performance because, as I said, you will have some sensitive packets, you will have some malicious packets, but you may also have other types of packets that are not labeled as any of those. So they will also be, their performance will also be worse. Okay, and another thing is that some significantly increase the hardware complexity. So that's the case of virtual channels, in which it will need one buffer for each virtual channel and will also include some muxes. On the other hand, we can have firewalls to stop the malicious traffic to reaching to its destination. However, these packets will still remain within the network. Another approach was monitoring the communication requests. In this case, the authors considered that before each of the transmissions, a request would have to be sent. And so they just count this amount of requests in a given time. And if it goes above a threshold, it is considered an attack. So as you see, this would be for the PIR-based attack. The other ones were monitoring the amount of packets that were received at the destination, so also for the same attack. So on the plus side, the reduction of the performance would be only while the detection has not finished and during the mitigation of the attack. And the bad thing would be that some detect the threat, but not the source, so the attack will not be neutralized. And most of the approaches in the literature target these PIR-based floating DOS attacks. So in our first approach, since we noticed that the objective of the attack was to increase the end-to-end delays of packets, then we were just monitoring that. We were timestamping each of the packets to monitor the end-to-end delay of each packet. And we also included a monitor in each of the input ports of the router so that we can have the maximum waiting time of the packet in each of the routers, and also the router where it waited the most. So this tail fleet was updated in each of the routers in the path so that at the destination, we will see which was the maximum waiting time. And with this, we will have a list of attack suspects, which I will show you next. This was published in NORCAS and also in TUS. Okay, then after that, we made some slight modifications to these monitors. And then we added to the tail fleet some information regarding the competitors, which is other inputs that were competing for the same output, and also which output they were competing for. So with this, we would know the direction of the malicious packets. And with this, we could even reduce the list of attack suspects, which I will show you here. So here's a simple example in which the processing element 8 is sending some data to processing element 6 using an XY deterministic routing. So you see first it goes through X and then goes to Y. So in this scenario, If the collision was detected in router 9, then only the attack suspect would be 9. But in the case of 10 or 6, we will have here 7 suspects of this attack. But if we discover the direction of this malicious traffic, then we can split this list into smaller lists, and then from 7 we can get these 4 suspects. This may not seem much here with this deterministic routing, but if we go to adaptive routing, we will have more options of routes, of paths. And in this case, you will see here that we can have at most 12 suspects, which is the case here at the path when it meets the collision at 6. And this could be divided into at most 7, which is almost half of the list. But also we can detect if it's 7 the actual attacker. Okay, so this both approaches were synthesized, and we had a small overhead of 17 and 23%, and power overhead of 5 and 9.4%. So the baseline that we took was the router from Project Bonfire, which was developed at TalTech, and it's available at GitHub, which is a minimalistic router. It only forwards data, but it doesn't have any type of security of quality of service. Okay, then after that, we went to attack low and slow denial of service. And for this, we were monitoring only the local input port, and we were able to reduce the structure of the packet so that we didn't need to add any additional fields to the template. And then what we did here was we were monitoring when a packet started or when a header came, and then we were just bypassing this data until the tail fleet came, and then the process started again. However, if our counter reported a timeout because of the interfleet delays going above a threshold, then what it did was generate a tail fleet, which will release the path of the communication, and then we'll go back to just dropping all the other fleets that came from this attacking packet or malicious packet. So first, we had to show that these low and slow DOS attacks were comparable to the floating denial of service attack, since these were new types of attacks in this context. And then we showed for packets that were 10 fleets long, that if we were increasing one interfleet delay, then this would be comparable to 25 fleets of the packet, and so on. After that, on the right, you can see the results with our countermeasure, which was the threshold was set to 5 clock cycles. So you see as the interfleet delay increases, then the mean end-to-end delay of other packets also increase. However, when it reaches 5, our countermeasure kills this malicious transmission, and then the mean end-to-end delay goes back to normal. Okay, this was also synthesized, and we had only a 2.4% of area overhead when comparing to the same router from Project Bonfire. And currently, we were working on this comparison between both floating denial of service attacks, since despite most of the other authors publishing or focusing on this PIR-based attack, we wanted to show that by using this round robin, this threat is neutralized. So you see here in our results that we were increasing the PIR, but then the only one that was affected by the attack was actually the attacker. The others remained the same. This is for single source attacks. Okay, and when we increase the length of the packet, we will see that the attacker here remains on his normal end-to-end delay. However, the entire network will suffer with this attack, and any other paths that collide with the path of the malicious traffic will see a worse impact. So this was presented in TUS this year and will be also presented in ISCAS. So for this, since we already know that the injection rate doesn't matter much, or if we have this round robin, then we focus only on the long packets. And then for this, we will have some monitors in the inputs that will register the length and the source of the last packet that was forward through this input port. And then we also have another block that will be monitoring which are the competitors with the packet that is waiting in that port. And then it will update the tailflit with the size and the source of the longest packet of the competitors. And once this reaches the destination, it could be reported to a global manager, which will take action. It will decide if it should neutralize the attack or if it is an allowed behavior. So these are the synthesis results. We need to see here that we have 3 types of routers, since the approaches are for each of the input ports. Then we have to see that corner routers such as 0, 3, 12, and 15 have only 3 ports, 2 connecting to the NoC and 1 to the processing elements, while edge routers such as 13 and 14 have 4 ports, and internal routers have 5 ports. So you see here that the area overhead was 32, 35, and 39, while power overhead went all the way to 72, which are not good results. However, at this point, we optimized the baseline, but we haven't yet optimized our approach. So in conclusion, DOS attack represent a threat or a live threat to the execution performance of NoC-based MPSoCs. DOS attack avoidance mechanisms increase the area and also may affect legitimate traffic. Also, low and slow denial of service attacks are equivalent in impact to floating DOS attacks. And packet-based round-robin arbitration is recommended for avoiding PIR-based floating DOS attacks. In our future work, we will develop new architectures for detecting and mitigating these types of communication threats, and also optimize the presented approaches and target distributed denial of service. Thank you very much. Any questions?